Hello, everyone.
All right.
Yes, sir. We're back
Hello.
1 year late. Yeah.
Yes. Yes, we are.
Yep. And we're
Hi,
back.
Dima. How have
Hi.
you been doing?
You know, been pretty rough this last year, but we're back to talk about some physics, right?
Yeah. This
Yeah.
time it's even harder physics.
Unfortunately, but you
Yeah.
guys are 1 year older too, and
Yep.
a 1 year smarter.
Yep.
Hopefully.
You're now in third grade, not second.
No. Yeah. It's a big year. I remember
So,
my third grade was a roller coaster.
why is that?
I moved continents, but
Oh, yeah.
yeah,
Casual.
it's a pretty small
No.
thing. Pretty small thing.
Normal Demo behavior.
Yeah, it just felt like it one day.
Yeah.
It's like when you in a video game when you click switch teams, you know, it's like one of those moments.
Yeah.
Yeah. But all right, Sai, what are we gonna be talking about today?
All right. So today we're going to be explaining multiple concepts in the Physics 2 curriculum. Now, some of these topics include electrostatic interactions, circuits and their behaviors, fluid pressures, fluid flow, the first law of thermodynamics, geometric optics, the double slit experiment, and the wave-particle duality, the photoelectric effect, and magnetic flux. Now, who are we going to be explaining these things to, Dima?
We kind of said this, guys, because it's gonna be to you guys, right? You're pretty young, third graders now, but that's just because you're young doesn't mean you're not smart. And we should be able to explain these pretty well to you guys. You're gonna have a lot of fun watching this, listening to this, reading this if you do that. I don't know, but yeah. But how are we gonna talk about these, right? Because these are pretty hard concepts, right? Really hard. Sai, what are we gonna do today?
So basically, we're going to be explaining a bunch of the equations that are found on the Physics 2 equation sheet. And just like our physics teacher, Mr. Restrepo, we're going to be using multiple diagrams to explain these concepts just so that you know what's actually going on and not just how to use them. And that makes it really easy when you're in a class like Physics 2 in the future, AP Physics 2, because you have things called FRQs and you kind of need to know what's going on and not just how to use things. So it will be beneficial for you once you get to high school if you're going to pursue a career path in physics or even any type of science. So yeah, basically we're going to be drawing a bunch of equations.
Yeah.
Drawing a bunch of pictures relating to equations.
And to sort of compare these equations, we're gonna make a tier list because those are usually fun, right? And usually they're pretty fun. Hopefully this one's pretty fun too. And we're just gonna sort these equations. Do we have a hard rubric for this? Of course we don't, because otherwise this wouldn't be this. This would be on the wrong channel. But primarily we're gonna grade these equations on how fun they are to work with, which is a very, very rigid term, though, I have to say. Very rigid. Very rigid. So, should we get started?
Yes. Yeah, let's get started. So first off, let's start with the equation F equals MA. Now,
hold up.
I'm sure most of you...
Hold, stop. Chill.
Are you going to cut it there?
I was going to cut it there for the Jamboard.
Okay.
So we're gonna transition to a Jamboard. So just start like now we're like now we're gonna be looking at a Jamboard. So it's like just explain the transition. Just start talking. Actually, wait.
Right.
We don't have a F equals MA, by the way.
Oh, we don't. We got rid of it.
Physics 2 only.
W.
All right.
Okay. What do we start? I don't even know how to read the thing. Did you share it with me or?
What thing?
All the equations we're using.
Oh, you have the screenshot on Discord, right?
Oh, wait. Yeah, I'll pull that up on my phone. Give me one sec. Discord shit. Okay, zoom in. Okay, that's row and stuff. Okay. All right.
Do you want me to start with here?
Sure. Yeah. Do you want to go over fluids or?
We're both gonna be going through it, I think.
Okay. All right.
Yeah. Right. 3, 2, 1. Ready?
Yep.
All right. That was a really fancy transition, I gotta say. You know, in 1 year of video, in 1 year, I was able to finally learn video editing. So that's great. And let's start with fluids, right? For the first unit. So, before we get into fluids, right? Because honestly, before I gotta say this real quick, fluids is one of my favorite units this entire year. So I'm gonna be kind of biased, but
And easiest as well, or that just might be a me opinion.
that is the reason why it's the most. That's why I like it. But so and the equations are pretty simple. But let's start with some of the concepts, like because to really understand these equations, you have to understand the concepts behind them. Because otherwise, it's like you're just trying to do math without knowing what the numbers mean, which at that point, there's no point in you doing the math, really. So, fluids, right? In fluids, specifically, we often talk about ideal fluids. And 1 second, this should hopefully start working. Ideal fluids, right? Fluids. We're going to say F. Fluids. So, Sai, can you name me the 3 parts of an ideal fluid?
I got you.
So,
So the first characteristic of an ideal fluid is that it's incompressible,
what does
meaning
that mean?
that it always has a constant density. And this basically means that,
One second.
as the equation
Hold up 1
rho,
second.
which stands for density.
1 second. I gotta fix my spelling. I am so sorry.
Oh, it's okay. It's okay. I'll let you take your time. Let me know when you're ready.
Yep. I might have learned video editing, but I did not learn how to spell things. You know what? We're just gonna write it out because my handwriting is impeccable.
Okay. All right.
Okay.
So,
1. Yep.
An incompressible fluid an ideal fluid needs to be incompressible, which basically means that it has a constant density. And this helps us in a lot of the equations because if density was changing because of other factors, then we would not be able to use some of these equations with the amount of ease that we use them with. And then the second the second characteristic of an ideal fluid will be covered by Dima.
All right. So we got it's incompressible, right? Second of all, there's no internal friction within a fluid, right? So no internal friction, right? So what does this mean, right? Well, so what does this mean? Like, right? Because why is having no internal friction important, right? Why is it important?
Viscosity.
Yeah, but why? Hold up. We're gonna cut this out.
Okay. No. I'll just start speaking.
No, because you already passed it over to me.
Sure. Okay. Just talk about how no internal friction is good because it means that it's a non-viscous. So it means that it's free flowing, which helps keep velocity the same during many of the
honestly, do we
situations.
Do we have to explain? We just say an ideal fluid is incompressible, no internal friction, and laminar flow, and just that.
Yeah, you can just say like it's not viscous. Yeah, just say it has no internal friction, meaning it's oh shoot.
It's non-viscous. It's no viscosity.
Yeah, meaning that it has no viscosity, so it's not gonna be really thick, or just like describe it,
1 second. Okay. All right. So the second part of an ideal fluid is that there's no internal friction, right? Once again, I apologize for this atrocious handwriting. I still haven't learned how to write in the last year, so that's a thing. But yes, ideal fluids do not have internal friction. And in physics, we have this fancy word for it named viscosity, which just means internal friction. And Ideal fluids obviously don't have that, so we call them non-viscous. And lastly, the third part of an ideal fluid is that it has laminar flow, which if you ever use the drain, you would know this one, right? Because you know how when you turn the water on, it looks like one continuous stream. Sai, you use yeah. Yeah. So then you know what laminar flow is. It's just that.
Sorry, I was drinking water.
Happens to the best of us.
Yes, it does.
Yes, it does. Well, now that we know what an ideal fluid is, let's get into the fun stuff, right? So let's go here. Let's get a blank board. And let's talk about pressure, right? So what is pressure? Let's think about it like this. Let's say we have this certain area, right? And thank you, Sai. And
My bad.
Oh, you're good. It was beautiful. It was a beautiful green line you had there.
Oh, it was green.
It was green. And let's say this is the bottom. This right here is the bottom of this box that I'm about to draw. And this box is open at the top. And there we go. No, I may not know how to write, but I can surely draw very well. So, and this right here, call this B. Or actually, since this is an area, let's call this A. This area A is the same as this area A. And let's say that in here, this is just water, right? We know that from we know from last year that because obviously we're assuming this is an Earth, right? Earth is right under this. And from last year, we know what gravity is, right? So that obviously means that the water exerts a downward force on the bottom of the box, right? So there's force of water on bottom of box, right? However, this force is over this whole area, right? Because it's not targeted at a specific point. So therefore, this whole area is sort of like it sort of feels the force. That's how we get to our first equation of P equals F over A, or pressure equals force over area, which makes sense, right? Just pressure is just a force distributed over an area, right? And this is our first equation, I believe, right?
Yes.
Yes. Yes, it is.
You might also want to explain density.
I'm sorry. I apologize for that. But you guys know what density is, right? That was a third grade science class, right? So, but
I
for
would
those
hope so.
But for those of you that don't, just density is just a property of a material. It is mass over volume, right? So let me draw it out. M over V. And it just really says how much stuff is in a certain amount of stuff, if that makes sense. It's how much stuff in there in how little space, essentially. And I often like to think of it as in terms of if you like make a really tight fist with your hand, right? It is very dense, right? But if you like make a small hole in it, right? So that you could like sort of like look through it even, there's less stuff. It's bigger, so the density is smaller. And that is the first equation of the one that we're going to be talking about, right? Now,
what is the variable that we use for density, Dima? I think that might be the only new part of the equation for our fellow third graders here.
Obviously, I think you guys use D for density, which makes sense. From last year, you should know, however, that physics does not make sense. So we use rho, which looks like I can't even draw it properly. I'm sorry. It looks like a very goofy P. And it kind of looks like that. And it looks like a P. It's pronounced rho. I often like just to not question things in physics and just assume that's how it is. Now, for the second, right? Because let's go back to our box example, right? We have this water. Let me see if I can actually draw it. We have this water pressing down, right? Obviously, the height of the water is gonna matter, right? Because more water, more mass, bigger force, right? And that is how we get to the second equation. The third equation and the second pressure equation of P equals P naught, which often is 0, but if there is an initial pressure, then it matters, plus rho, which we now know, G, which you guys know from last year, and H, which just means height, the height of this water. So there we go. But now let's talk about how we can calculate the force of this. So, Sai, do you want to talk about that?
Calculate the force as in the force of buoyancy?
Yes, exactly. The buoyant
All
force.
right.
So,
So the force of buoyancy basically can be described through the equation FB equals rho times V times G, which also means
sorry,
density.
Hold up. We're gonna cut. Are you on the third slide, or am I tripping?
Yeah, I'm on third slide.
I don't see any. Did you draw anything?
No, I'll draw it.
I'm retarded.
Right?
My bad. All right. Just start.
No, you're good.
So buoyant force.
Should I draw the equation out?
Yeah, you should like make it.
Okay. Yeah, I'll draw it out. All right, let's go again.
All right.
All right.
Hold up. After this one, we're gonna go back to the tier list to sort those equations.
Okay. All right.
So
I'll do a force of buoyancy and then continue to flow and then maybe Bernoulli as well.
do those, and then we're gonna go back. Right. So.
All right. Cool.
So yes, exactly, the buoyant force.
All right. So the force of buoyancy can be described as rho times V times G, which basically means density, rho's density, times volume, which is V, and then gravity, which is G. Now, gravity can also be subbed in as 10 because I'm assuming that all of us are on Earth. So 10 times G times rho times V. Now, the force of buoyancy basically talks about the force that the water has on the object. And this force is usually used in scenarios where a boat is floating in water. Now, the only reason that it floats instead of sinking due to gravity is actually due to the buoyant force. Now, we can sub in density for the density of the fluid that the object is in, which let's just assume is water. And then we can also sub in volume as the amount of space taken up by the object in the fluid. So I know that sounds a bit hard to sort of visualize, so I'm going to be drawing a picture. So say this is a lot of water, right? And say you got an object in the water. Now let's just make the water one straight level line, right? But this basically is the water. And then in another color, let's say green, I'm going to be drawing the object. Now this is the object. Now, rho would be the density of the fluid as stated before. So that's just going to be whatever is, here. And then we would find V by finding out this amount of space. So not the total volume of the object, but rather the only volume of the object that is submerged in the fluid. And as that volume increases, as the object is deeper in water, the buoyant force will also increase. And if the buoyant force is higher than gravity on the object, then it will cause the object to float up. So when an object floats on a liquid, that means that the force of buoyancy equals the force of Earth on object.
Water on
And-
object, sorry.
On what?
It will be water on object. Because buoyant force it's a third law pair, which you guys know from last year, right? So it's actually, essentially, the object is pushing down with the same force on the water as the water is pushing the object back. So,
Wait.
what?
Oh, yeah, that makes sense. Yeah.
So,
Because
again, physics is hard
force
and
of-
we all make
what's up?
mistakes. Just keep going.
No, it ain't a mistake. Because, let me explain this to you this way. Force of Earth on object also equals the force of object on water. Because as the Earth pushes the block down, the same amount of force will be translated from the block to the water. So by using, my algebra skills, force of buoyancy can equal force of object on water, which is what I think Dima was trying to get at. Is that correct?
I'm sorry. Yep. That is
Alright,
what I
cool,
was
cool,
trying
cool.
to get at.
All right. So now let's go to another equation that pertains to fluids. So now we're going to be talking about continuity of flow. Let me create a new frame. So continuity of flow can be described through the equation A1 V1 equals A2 V2. Now, A is going to be the cross-sectional area at which a fluid is going through, and V will be the velocity of the fluid moving through certain objects like pipes. So that also is probably pretty hard to visualize as a third grader. So let me draw a quick diagram. So imagine you have a pipe, and in this pipe, you have a lot of water flowing through, and the water is flowing through in this direction, left to right. So by cross-sectional area, what I'm getting at is, let's look at this pipe as a circle, and say the water's coming at your face, right? So as the water is shooting in your direction, if you can visualize that properly, that means that the cross-sectional area is basically the area of the pipe. And this can be calculated through, A equals pi r squared, which isn't an actual equation that we're going to cover on our tier list, but it is useful to have once in a while in physics when we're talking about cross-sectional area.
Or if you're feeling extra spicy and you're really advanced, and maybe once you get into fourth grade, you can learn calculus to find this through calculus instead of plugging in this. But this usually works pretty well too. Sorry.
Yes. Gotta love calculus, right, Dima?
We love calculus here.
Yes, we love calculus.
Stay tuned for next year when we actually will be talking about calculus.
Oh gosh, that would be amazing. I'm sure of it.
Yep, we're sure gonna love it.
All right. So this was the cross-sectional area that I was talking about, and velocity is just the speed at which the fluid is moving through the pipe. So basically, the main concept that this gets at is the flow rate is the same. So the same amount of molecules of water will go through the pipe in any given point in time. So say, for example, I'll just put a random number out there. Here, there is 10 water molecules moving through at 1 second. Then here, there will also be 10 water molecules moving through in 1 second. So how this is accomplished, let's look at it like this. So basically, there is a straight pipe, right? This is a straight pipe. So it's relatively simple. As the area stays the same, its velocity will also stay the same, because that is basically what could change the molecules of water moving through the pipe. And since that's not being changed, the area and velocity do not need to be changed as well.
In other words, I know that was a very wordy explanation, but essentially, we had say A1 is equal to A2, and therefore V1 also is equal to V2. That's essentially it.
Exactly. So let's say the area was decreasing. Now, how this would happen is, let's say the pipe is, having a certain area of this, and it becomes really small. So as the area becomes really small, we still need the flow rate to be the same, which means that we still need 10 molecules of water to be moving at this point for 1 second, and we still need 10 molecules of water to be moving at this side for 1 second. But since the area is smaller, it means that more molecules of water need to go through here at the same time, which is where velocity increases, because as area decreases, velocity needs to increase in order to keep the product of AV the same on both sides. So another example of this could be when the pipe is, at a constant area, and then the area increases, right? So as the area increases, we still need the same amount of water molecules to move in either place in the pipe. So in order for that to happen, we need velocity to decrease as the area increases. So at this point, velocity would be less because area is more. And at this point, velocity would be more because area is less. So it's pretty simple, really, in all the questions you're going to get about this. And this is one of the easier concepts to learn in the fluids unit in physics. But now we're going to put it all together through an equation called Bernoulli's equation.
Yep.
I think that's what it's called, right, Dima?
It is Bernoulli's equation. It is, I gotta say it real quick, my least favorite equation in this unit, just because of how long it is. It even takes up 2 lines of the equation sheet, which I mean, come on. But
way too long.
Yeah, but once you get down to it, it's actually pretty simple, and it's just essentially the concept of conservation. Because as I said, if in the beginning, if you have 10 molecules moving here, you need 10 molecules moving here, no matter what changes. And it essentially puts everything we talked about, and it just says, if the fluid moves, it has to move the same way, no matter what changes about the pipe. Like the pipe could get bigger, the fluid's got to move faster. That's fine.
Yes, sir.
We just relate this to energy, right? Because if you remember gravitational potential energy from last year, so height, if the height decreases, some other energy has to increase. And we just sort of relate this into fluid form. So I think Sai is drawing it out right now.
Yep, just trying to get a head start because the equation's so long.
I'm gonna write the second line for you, just because how long it is.
Thank you. I appreciate it.
Yep.
Rho V1 squared equals whatever's on the bottom. Draw a weird arrow. But yeah, that about sums it up. So basically what this is getting at is conservation, or it's similar to conservation of energy. So we can think of rho G Y1 as sort of gravitational energy, right? And then we can think of 1/2 rho V squared as kinetic energy, because kinetic energy's equation is 1/2 mv squared. And basically all you're doing is you're subbing in rho for m. So it's kind of like translating things from kinetic form or like linear form, like however you want to say it, physics 1 to physics 2, basically, as you're moving it to liquids and fluids. So fluids, not liquids, fluids.
Because if we haven't said this before, fluids can be gases.
Yeah, we don't like gases.
We don't like gases.
Actually,
though.
we do. We
No.
like gases.
We like it.
Gases have a nice equation.
They have a nice equation, but when you talk about gases as fluids, that's not fun. So
That is not fun.
that's
I
not
agree.
fun, and they're just like kind of like there. But as I is saying, yes, this is an important concept because if you really look at physics 2, it's not very different from physics 1. You get some couple new equations, but it's really just you're applying that same thinking, those same concepts in a different way. So
Yes.
let's sort these equations because obviously some of them are fun, some of them are not. Right? So let's do this. What do you? Let's start with. Let's start with Bernoulli's equation. Let's start with the big boy. What do you think about it? In terms of
That
how
has
fun
got
it
to
is.
be a D or an F.
Really?
Maybe a. I would say it's a concept. It's sort of unimportant concept, but it's also kind of a pain to write out.
Yeah.
But it is a bit important. So maybe I take that back. Not an F. Maybe a C or a D.
If we're, I think we're doing it on how fun it is. It's on a concept basis. It's a pretty easy concept to understand, right? Like just things stay the same. You can change some things. The overall thing has to stay the same. As a concept,
conservation.
Conservation. As a concept, it's not hard. But it's not really fun to write out. This was on the in the EP test actually, on the AP FRQs, and like it was alright.
Can we talk about the AP test? Is it
Actually?
legal?
Is it? Oh no.
Is it?
Oh no.
Oh well, it may or may not have been on the AP test. We're not really sure actually.
Yeah. If you want to check the FRQs for yourself, which they may or may not be available online at the College Board website, you can check it out. But we may or may not be saying that this was on our FRQs. And
yes.
as a question,
or maybe.
Yep. And in this hypothetical scenario where it was on this hypothetical test, it was hypothetically a not too hard of a question, right?
Yeah.
Yeah. So just to move on and to not get into any sort of troubles, I would say a D is probably fair, right?
Yes.
Say so, because in terms of how fun it is, it's not. So.
Well said.
All right, now to some more fun equations. Any that you want to talk about first? Order.
I think flow or continuity of flow, which is A1 V1 equals A2 V2, needs to be on A or an S tier.
Really?
Just because it's a really easy concept. We've had multiple questions on it, and we usually get the answer pretty quickly just because of how well it's been taught to us by Mr. Strepo, and also due to the fact that how easy it is, and it's not really that long, and it only has two variables that we really need to worry about. So due to its simplicity, how much we've used it, and just, how much effort it takes to actually use it, I would say it's pretty up there on how fun it can be.
I do think it's up there, but I know my memory is it's still pretty bad. When year changed, it did not improve at all. I don't actually remember using this one much. I know it exists. It came up on the fluids test, but I don't remember using it after.
Yeah, you're right.
Yeah.
On the hypothetical AP test, it was not really as present, but during the fluids unit test, it definitely was there multiple times.
Nor in any of the practices I took, it never showed up. So.
Oh, right.
Yep. So, I cannot put it in A. I just because of that, like, it's nice, it's there. It's like when you go to a store, it's like you I went to Barnes and Noble actually today, and it's like this was not me today, to clarify. I got a book I liked, but it's like it's one of those things you buy to just look sophisticated. It's like this, but do you really use it? No. It's like just one of those things.
Yeah.
Yeah. So I would say either a B or C for this one.
Yeah.
So,
I would say a B.
All right, let's put it at a B for now.
All right.
All right. Now let's talk about density, right? It's a pretty easy one. I mean, I think you guys already knew about this one. We just a fancy letter. Again, it's a simple concept. It doesn't show up at all in physics 2. You know it's there because it's just what fluids do. But it's you don't. It's actually what every element does. Every element has a density.
You can use it in a few derivations, though.
That's true.
That's usually the only place where they're really, really important. But other than that, I wouldn't really see you putting it down as justification for an FRQ because it's just basic knowledge. I mean, everyone knows what density is.
It's really just you know what division is. It's mass over velocity. Like you know how to divide, right?
Yeah.
Which I mean, so I feel like I think it's better than Bernoulli because it's more fun, right?
It is more fun.
It's more fun. Let's give it a C for now. And next, let's talk about pressure, right? Because we're talking about division sign. It's again just a single division sign. However, I like this one a lot more because it's.
Oh yeah.
Yeah. Because it actually starts to make you think, right? Because let me clear that, and it really starts to make you think because. First of all, it just explains the concept very well, which I mean, I guess the density equation does that too. But this one you actually do use a lot more because, and often you're going to use some F equals ma or some other, you're going to plug something else for force. And that helps with a lot of calculations when you're solving for the pressure, which is quite nice.
Yes.
So what do you think about it, Sai?
I would say that P equals FA is definitely used often, and it's just one of those things that you just need to know if you're going to get through fluids. It's like it's essential to everything else you're going to know.
If there's if there's one fluid equation that you should know, it's going to be this one.
Yeah. So, and it's not that hard to learn. And it definitely isn't that hard to use once you've learned it. So it is pretty fun. It is pretty enjoyable to actually use it.
And it's pretty easy. So
I would give it an A.
I agree with that. I think it's a strong A. And then let's talk about the other for pressure equation because this is just like it talks about pressure due to depth. Which I guess if you're into oceans, like that is pretty cool. That now you understand sort of why that is. Why you talk about like the pressure at the bottom of the ocean is so high. Now you kind of can like put it into numbers, which is nice to think about. But apart from that, it's like it's in terms of enjoyableness, it's not exactly enjoyable. I mean, it's another one of those it's pretty easy. Again, there are no squares as in the Bernoulli equation, but it's not anything special.
Right. I would say that it is also used pretty frequently, especially in a lot of practice FRQs that we did. And I think it's also been used in multiple tests that we've taken. But I don't know. I would definitely rank it lower than the original pressure equation, but it isn't really that bad to use. It's pretty simple once you know the concept, just like a lot of these equations. And it's also just important, I would say, for specific types of problems that you're going to come across at least a few of them during your AP test. And multiple choice or FRQs. So I would say it's maybe a B.
Really, a B. That's quite high, but I'm not mad about it. I think a B is. I would say low B, high C. I would say is fair.
Yeah.
So then buoyant force. You want to talk about this one?
Buoyant force. Buoyant force is.
It is quite.
My memory is kind of a bit bad right now, just because it's been a while since the AP test. But buoyant force
No, we're
is
not
probably
sorry.
something that you're gonna
Sorry.
have to know just because.
For legal reasons, we are required to say that we do not know if this came up on the test. You know, you said this was after the EP test. Your memory is hazy on this. This was for the studying for the EP test, not necessarily for the content of the EP test, which may or may not have included this equation.
Right. Maybe.
Maybe. We don't know. We don't know.
We don't know. We don't know, right? Because we forgot. Yeah. But I would say if you're gonna encounter P equals P naught plus rho GH, you will probably encounter buoyant force in that same problem as well. If it's an FRQ or if it's a group of multiple choice questions, then usually you're gonna have to use both of those equations. So I would rank it pretty similar to what we ranked the previous equation.
Right, so a B, I guess.
Yeah.
Okay.
Low B. Yeah.
Lil B. It's like a rapper name. Lil B.
Yes.
Yes. All right. Well, that's fluids done. I mean, I guess overall as a unit, it's a pretty good unit. I liked it again.
Yeah.
Not too many complex equations, and the ones that like are a pain to work with. Most of it is conceptual, which personally I really like. And that's about it. Any thoughts about fluids as a whole?
Fluids are great, and I know physics teachers do it differently, but our physics teacher taught us fluids first, so it was actually one of the easiest units that we've been through, and it is a pretty good introduction to physics 2 as a whole. All right, so now we're going to be talking about thermodynamics. Now, thermodynamics was the second unit in our physics curriculum, at least in the order that we attacked it. So let's get started with some of the equations that we have in thermodynamics.
Yep.
So, Dima, where do you think is a good place to start for thermodynamics?
So we're gonna, in the explanation part of it, we're gonna do a similar thing as we did in the fluids part. We're gonna talk about some concepts to you guys. You're gonna understand them. We're gonna talk about how equations work. We're gonna sort them, right? It's a very, very similar thing. So we talked about ideal fluids. Let's talk about an ideal gas, right? Now you might be sitting, and here we'll make a sticky note. So now that I actually know how to type in this. So ideal gas, right? What are the parts of an ideal gas? Number one, it has negligible intermolecular interactions, right? And so what this really means is that the interactions between individual particles of the gas particles. So the same gas, its own particles, we don't have to worry about how they interact. Now we know that they do interact, but it's negligible, and we don't have to worry about it, right? Then, an ideal gas has completely elastic collisions. We'll write it like this. Again, I still don't know how to spell, but at least I know how to type now. So it has elastic collisions now. From last year, you remember that means that an elastic collision is one during which energy is conserved, right? And we said this because it's gonna make some of the math easier. Just that, really. And I mean, obviously, an ideal gas takes the volume of its container. We can put that down. Volume of container. And that is really it, if I remember properly, right, Sai? I don't think I'm forgetting anything.
No, I think that's all for ideal gases.
Okay. Now, these ideal gases have a special. With these assumptions, we can write out an equation that we call the ideal gas law, which is the holy grail of the gas unit, and everything sort of stems from it. And that is pressure times volume equals N, which stands for the number of moles of gas, or actually, yeah, it stands for number of moles of gas, and we're going to come back to this though. And R, which is a constant that varies depending on your other units. But don't really worry about this. This is usually given by the problem. And T, which is temperature in kelvins. Yes. All right, and that is really it. It sort of relates these. There's a whole lot of history lore if you're interested into that. There's Avogadro's law, Gauss's law, like a lot of laws, Charles' law, Boyle's law. It really goes in depth, but they all sort of relate this whole thing, and this is like the holy grail of gases. And
Yeah.
And yeah. So Sai, you want to continue?
Sure, yeah. So another big concept that's really important in thermodynamics would have to be work equals negative pressure times change in velocity. And this basically is a reference to PV diagrams, as we call it. So
Change in
PV
volume,
diagrams.
I think you said velocity. Change in volume. It's change in volume. Sorry about that.
Oh, change of volume. My bad.
It's V.
So,
I'm sorry. I'm gonna go on for a little rant here, but throughout this video, you're gonna notice that we're gonna use the letter Q a lot, and for that, we deeply apologize. But when you don't know what a variable is, the letter for the variable is, it's in physics too. It's probably Q.
yeah.
I'm gonna throw it out there. It happens a lot. It's no big mistake. Just there's only so many letters we can use.
Yes. So, back to what I was saying. PV diagrams. So work equals negative pressure times change in velocity. Right.
Volume. Not velocity.
Yeah. change in volume. Okay. So basically, if a gas is at some pressure and some volume, let's say it's at a really high pressure and a really low volume, and let's say that something is being done to it to increase its volume but keep the pressure the same. So here we can see that pressure is positive, so it would be negative pressure, and that's multiplied by a change in velocity. The change in velocity is positive because velocity is increasing, because here's 0, 0, and here's some other numbers basically, and it's increasing left to right. So we can tell that there's a positive change in velocity, which means that there's negative work being done. But this can be confusing for some people, because if volume's increasing, and why would work be negative? Well, it's pretty simple. We're looking at work in terms of work exerted on the gas and not work that the gas is doing. So those are opposites of each other, and they can be confusing, but you just have to know that if if volume is increasing, then negative work is being done.
Yep. And funnily enough, these PV diagrams also relate back to the Pivnerd equation, because obviously everything's related, and a change here, a change like this line moving left to right, that means also temperature would have to change, which is just this nice thing. And
speaking of that, Dima, do you want to talk about change in U equals Q plus W?
Oh yes, the first law of thermodynamics. Here, let me open up a new frame. So first law of thermodynamics. It sounds a lot more complicated than it actually means. What it really means is, as you kind of said, delta U, which stands for the internal energy, and that's gonna stay consistent throughout this video, is equal to Q, and that's not the only time we're gonna see this letter, but it is the first time we see it. And in this case, it means energy transferred to a system by heating, plus work, which Sai just defined for us. It's the plus sign and work. And that's essentially it. Now, we can relate this back to the PV diagrams because, and to the different processes, because in PV diagrams, let me draw a new one so I don't have to go back and forth. PV diagrams, PV, we have a couple ways of transitioning from one state to another, right? We can either keep pressure constant, which is an isobaric process, which is what Sai drew. We have an isovolumetric, or also called an isochoric, which is when the volume stays constant. Then we have an isothermal, which, as you might guess, is when the temperature stays constant, and an adiabatic, when the energy stays constant. This is supposed to be one continuous line. I am sorry. It's just drawing it with the mouse is pretty hard. But
Yeah,
essentially,
adiabatic is just steeper.
yeah,
That's the only
yeah,
difference,
it's the
basically.
It's this one, the bottom one. And obviously, adiabatic means that delta U must equal 0. Isothermal must mean that Q, because it's heat, equals 0. And obviously, from this equation, we know that if delta V is 0, which means the volume doesn't change, so in an isovolumetric process, the work is going to be 0. And so this, essentially, you can, first off, thermodynamics, it's, I know it sounds really hard, really complex to understand, but in reality, it's just a PV diagram, essentially. And
Yeah.
now, we talked about the ideal gas law, but this is on a very big scale, right? Or as big as you can get with gases. However, when you look at the individual atom, we change up some of the constants a little. And this was done by Maxwell Boltzmann. You don't really understand, obviously, it's not, as you go further into physics and as you get older, you could get to learn more about him and his brilliant mind. But for now, you just have to know that the kinetic energy is equal to 3 halves. Oh, sorry, that's a different one. I am, am getting better at writing, not better at reading, unfortunately. But it's equals to N times the Boltzmann's constant times temperature. And this sort of just change up some constants. We get rid of R for Boltzmann's constant, which I believe, I'm forgetting what Boltzmann's constant is. Could you remind me, Sai? I'm forgetting. It's like 1.38 times something. 10 to the negative third. Yeah, all right. Sorry about that. But that's really it. And it's a lot simpler. And I think it was just an extension of that. And that's about it. And the equation that I was talking about is for the kinetic energy of a molecule, which is 3 halves times the Boltzmann's constant times the temperature. And with this, we sort of finally understand that really temperature is just a measure of the kinetic energy. And yeah, that's it for thermodynamics. Pretty short unit.
I think we might have one more equation.
That's my bad.
I can go over that real quick. Also,
Okay.
One more thing, just like a general tip to have in mind is temperature is always going to be in Kelvin. So I know that as third graders, Kelvin's not really something that you all are familiar to, but it's basically 273 degrees plus the amount of degrees in Celsius. It's not really that hard. You get used to it once you're in high school, but just always remember that unless specified, temperature is always going to be in Kelvin in most of your science classes. So, yeah.
Yep.
So one equation for thermodynamics that I think we should cover would be Q over change in T, change in time, equals K, A, change in temperature over length. A stands for area and Q stands for heat. So this is basically talking about thermal conductivity, right, Dima?
Yes, where obviously if you put two objects together, one is hotter, one is colder, they're gonna get somewhere in the middle.
right? And they both will end up in the same temperature, which is what thermal equilibrium is. Yeah, so basically the area and the length are variables that you get from the specific object that the heat is transferring over. And few overchange T is basically talking about, how temperatures moving in relation to time, how temperatures changing in relation to time. And yeah, that's basically it. Is there anything that I missed, Dima? They want to fill in?
Big L, correct me if I'm wrong, but doesn't that stand for thickness?
Wait up, let me check. Yeah, thickness.
Yeah.
Sorry, yeah, thickness.
Again,
Yeah,
it's the same thing of us only having so many letters, but yeah.
Yeah, I don't know why. I think
Honestly,
they chose L for horizontal or like length, but I don't know. I think it's weird. It's just weird. I can't find a way to explain it. I don't know how
I guess
the physicist who came up with it is gonna explain
but
it.
then I guess you already have a big T for temperature, little t for time. But it's like, I don't understand. Because, like, length intuitively does make sense too, but
You just have to look at it from a different way.
Yeah, exactly. Just, like, rotate it around. It's length,
Yeah.
you know?
Exactly.
Honestly, we should just create a new alphabet with more letters.
I agree.
That's the only way to solve it, but
yeah, that's the only way.
I mean, that is the only way to get through thermodynamics, which we just did. So
somehow, man.
How would you?
All right.
I enjoyed this unit personally. I gotta say, first of all, I think I'm gonna go with I think it's not really a hot take, but I think the ideal gas law Pivnert has to go into the S tier.
Yes, I agree, 100%.
It is, when in doubt, when you have a gas, just use Pivnert. More often than not, you're gonna be right.
So fun. There's so much plug and chug, it's just a lot of practice that you need with it. There's not really too much conceptual thinking that goes along with it, which makes it really easy to learn.
Like I've had questions where I'm like, what is going on? And I'm like, no, it's a gas. Maybe like Pavner will work, surely, right?
Surely.
And then I get an answer that makes sense, and I'm like, oh yeah, no, I knew that, right? Like, of course, yeah, no, I remember this, right? So
yep.
It makes me seem a lot smarter than I actually am, which is always a great thing.
Yep. So whenever you're in doubt and the question has to do with a gas, try your best to fit it into Pivner, and you'll find a way. And it's also really helpful, just because if you're talking about how, say, one of those variables are being manipulated, you can clearly sub in things that are not changing as one, and then you can see how another variable changes. And I know that sounded a bit confusing, but I forgot what the name of it's called. It's like proportional something.
Proportional analysis, I think. Basically,
yeah.
If one side of the equation changes by a factor of 2, so does the other, because then it would not be an equation.
Right. Again, they always need to be equal.
Again, English makes things sound unnecessarily sophisticated. But yeah. That's why we should, honestly, to fix this like new alphabet thing, just go back to pure Latin, honestly.
Pure Latin.
Yes, Latin.
You already know.
Yep. But yeah, that is that. All the other equations seem like pretty okay. I didn't really have any strong feelings about them.
Yeah, they seem pretty average.
Kind of just want to put them all in the C tier, to be honest.
Yeah.
Okay.
Maybe, I don't know, we could have the work function was always a bit goofy, or not work function. The work equation was always a bit goofy. It took a very long time for us to understand that one.
Yeah, that's true. We'll put that in the tier. We'll put that in the tier. It deserves it.
Yeah.
It deserves it. And yeah, that is thermodynamics done. Very short unit.
Very short.
Yep.
All right. What's the next unit, Dima?
Next unit, I believe it is magnetism, right? Actually, no,
Yeah,
electrostatics.
magnetism.
Electrostatics, sorry. Getting ahead of
We
myself.
could combine the both of them. I mean, they're
That's
pretty
true.
similar.
That's true. All right, I'm gonna say this real quick because this is gonna be very seen in my bias. I hated these units. I absolutely hated them.
What?
Electrostatics was my least favorite unit. Just the concepts I couldn't grasp for a really long time. Yeah,
Electrostatics was the best unit, Dima.
that is an objectively wrong opinion. Absolutely heretical, if I do say so myself. The FRQ that may or may not have been on electrostatics, I completely bombed. So or in
Was that the last one?
yeah.
That was the only one I got right. Let's go. No, I'm kidding.
So yeah, you're really getting to see both sides of the coin here. You get to see an electrostatics fan and an electrostatics hater here.
Yeah.
Let's get into this. So, let's start with, I guess, the biggest equation probably, which is, if you just watched our last year's video, this equation is gonna look very similar to you. Let me see if the pen is gonna work. There we go. So we have F equals K, and as I'm writing it out, I want you to think of the equation that this looks very similar to. And Sai, if you want to say the answer, go ahead.
Gravitational.
Yes.
Something.
Yes.
I forgot what it's called. I forgot the exact name.
Newton's gravity. Yep, and it's essentially just a ripoff of it because essentially gravity and electrostatical forces are just really two sides of the same coin, and just two perspectives looking at, and that's why this is very similar. This also introduces us to a new unit called coulombs, which is a really big unit, and that's why this constant is going to get really big. But that's about it. It just tells us the attraction between two charged particles. Obviously, the further apart they are, the weaker the attraction. It's another one of those inverse or squared laws. And it's like, I guess it's fun. I had this one in my dreams, so I'm very biased against this equation. Like I remember sleeping just in the middle of this unit, and I just remember seeing this like in one of my dreams. And
Dang.
yeah.
You just loved electrostatics that much. You were dreaming about it.
Yeah, definitely. Yeah. So
yeah.
Yeah, I mean this happened. So,
sure did.
Yeah. So obviously, positive particle gets attracted to a negative particle. Really, I mean, it's just very similar, right? These are going to be attracted to each other. And yeah, these are. Is there anything you want to talk about this unit?
Not specifically about the force of the electric force between two charges. No. We could go on to fields, though, right?
Yeah. If you want to talk about fields,
all right.
We'll create a new thing for that. Yeah.
All right. So the next equation that we're going to talk about is field, which is E. The strength of the field equals 1 over 4 pi epsilon naught, which is a constant called, if I'm not mistaken, it's called vacuum. No, it's not called that.
It stands
for Coulomb's law constant. It's Coulomb's law constant.
Yeah, which is the one that we used in the previous frame.
Right. So Coulomb's law constant can either be 1 over 4 pi epsilon naught, or it can be 9 to the power of 9. So those two are kind of interchangeable. But basically this is then multiplied with the it is then multiplied with Q,
Yeah, absolute value
I'm gonna undo that.
over r squared.
Q over r squared, and this Q is an absolute value because we don't want the sign of the charge to really say anything about the field, because the field will also be absolute value because we're only measuring the strength of the field.
Yep. And
so basically this is
if
talking about how
sorry.
the strength of the field will decrease as the distance from the charge increases. And it also talks about how the strength of the field will increase as the strength of the charge increases. So yeah, that's about it for the functionality of this equation. Do you have anything else to add, Dima?
Well, it's just adding on to it. It's derived from this equation, which equals F over E over Q, which is, as you can see, one of the Q's will cancel out from the previous equation on the previous slide right here, Coulomb's law, and that's how we get it. So this, if you see this equation, it's just this. I don't really have any thoughts about it. We didn't use it that much. It's a good concept to understand, though. Obviously, it's another one of those inverse squared equations where the bigger the distance, the weaker the energy, the strength of the field, the weaker the interactions between the molecules, the particles. So there are some important concepts in here, but overall, it does not stand out to me.
Yeah, I agree. All right. Are there any other specific equations that we need to cover for electrostatics?
I don't think so. We can just talk about magnetism real quick then, right? Let's check. Electrostatics, you said, right?
Yes.
We could talk about
B. We could talk about B, right?
That would be magnetic.
The magnetic field.
Yeah. Draw some field lines then. Let's see this.
Oh yeah, we should probably do that.
We should.
All right. So basically, a field line. If I'm assuming most third graders in America don't know what a field line is, but for those that do, here's a quick recap. So basically, you have a charge, and that charge is going to have field lines. Say this charge is, let me do something real quick. Say this charge is positive, right? It's a positive charge. And this means that the field lines will be pointing away from the charge in all directions. Don't mind the length of my arrows. That's just a mistake, but imagine the length of the arrows are all the same because the strength of the field is the same in all directions. However, it does decrease evenly as it gets farther away from the charge, as we stated from the equations before. And the reason why these field lines point outward is because field lines basically show the direction of a positive charge if it comes in contact with another charge. So we call it the test charge. A test charge is massless and it doesn't really affect anything, but it's just positive. Test charge, and it's basically positive, and two positives would repel from each other, right? So say there's a test charge right here. That test charge would go away from this proton. So since it would go away from it, the field line points out. But say we were talking about a negative charge. If a positive charge came into contact with a positive test charge came in contact with a negative charge, then it would go towards the negative charge, which is why the field lines would be in the opposite direction if the sign of the charge was opposite. So yeah, that's just a quick intro to field lines. Dima, is there anything you want to add?
Not really. I mean, it was a great explanation. I just want to briefly mention that this concept of negatives going against field lines. So, for example, in this drawing, if we introduced a negative charge, and if my pen would work, if we introduce a negative charge, it would go against the field line, because obviously it's the opposite charge of a positive particle. Therefore, an electron will always go against field lines, this is going to become really important in magnetism, which, speaking of, let's get into magnetism, right?
Yeah.
Which is, as we're going to see, those two are very, actually, let's talk about how they're connected, right? So, and it's actually connected through a concept called Faraday's law, which, even though these were some of my least favorite units, this is one of my favorite concepts in all of physics too. So Faraday's law, and essentially it is just that the potential, which is, we're going to get into this more with circuits where it's going to be very prevalent, but it's essentially just how much charge, right? Just how much. It's measured in volts. It tells you how strong a battery is, for example, and we're really going to get to that in just a second. But just think about this as just how much charge there is. And this equals to the change in flux, which is we represent with the letter phi, of the field over the change in time. And now you might be thinking, well, what is flux? It sounds like a made up word. Well, and to that, I gotta say that all words are made up. So,
amazing.
Yep, that's a great analysis by me. Thank you very much. But what is flux, right? Well, let's say we have a certain area, right? Let's call it A, and pretend this is a closed shape. Just a normal rectangle, we have A. And let's say we have just a field here, right? Let's say this is represented here. It's going into this. And essentially, flux is how much of the field passes through a certain area. So obviously here would be just measure of the field times area. So this is why we represent it as flux is equal to BA, where B is always going to stand for the magnetic field, just so you know. And area is represented by A, obviously. Now, there's a better version of this equation which we use, because in reality, as we saw, field lines are lines, right? And lines have directions, obviously, right? Otherwise they would not be lines. Therefore, we only want to take, so let's say this is another view, a side-on view of the area A. And let's say we have a line that goes like this, right? We only want to take the component of this line, of this vector, you could say, that goes like this. And that's why we include cosine of theta here. And that is flux. Now, the cool thing about Faraday's law and this is that the fact that there is an EMF, or an electromotive force, means that we can induce a current. And that means that by changing a magnetic field, which I'm skipping around right now, but let me see. But since if flux changes, right, and the area doesn't change, that means the field changes, right? So a changing magnetic field can create a current. So that means that inherently in a magnetic field and an electric field are existing within each other. And just briefly, I understand this is some very abstract concepts. I like to think of flux as like just a pool. So just imagine you and a couple of friends are in a pool, right? that's flux. And then the electromotive force is the splashes that you make in the water. So for example, you could have a lot of flux. You could have 15 people in one pool. But if you guys are just standing there, the flux doesn't change and there's no splashes. However, even if one person dives in, now there's a splash. And now the flux changes, so you have an electromotive force. And I find this concept just to be really cool because you can, just by moving a magnet around, you can create a current, and that's how cars are made, that's how generators are made, that's how electric motors are made, if you just reverse it the other way. So if you, and a current can cause movement, and I just find this to be really cool. So there's that. I think that covers quite a lot of equations, but all of these are very much connected.
Yep.
And so then some other ones that honestly we could probably just well, there's a couple other ones, important ones that I guess we should cover. So the force caused by a magnetic field is equal to, I'm actually just gonna go to a new slide. The force caused by a magnetic field, let's call it Fm, is equal to charge. Again, we see Q is used as charge, times the V, which stands for speed, so speed of the moving particle, times the magnetic field, right? Again, the way you remember this is that a moving charged particle creates a magnetic field. Correct me if I'm wrong, but a stationary particle creates an electric field.
Yes.
I believe so. And there we go. That's pretty much it. And just like with the last one, since we only taking one component of this vector, we use the sine theta here. And that is it for that.
A particle needs to be moving to create a magnetic field, by the way.
Oh, yes. That's, I believe I said that, but I actually forgot we can represent this with a separate equation, right? So I briefly talked about current, but let's define current, right? Current is really just this, how many particles move per time. It's just, essentially think of it like speed. It's the speed of a particle. So it's the speed of charged particles. And we represent current with the letter I. Now, how does this relate to magnetic fields, and why does only a moving particle create a magnetic field? Well, let's say we have B, which is our magnetic field, represented by mu naught, which is a constant, over 2 pi I over R. And as you guessed, I is the current. So only a moving particle can create a magnetic field. And that's really it when it comes to magnetism. I mean, you do have one extra equation in the fact that electromotive force is equal to the magnetic field times the length, is it of a, is it a rod? Or is it's a solenoid, right? I'm forgetting this one.
I'm not sure. For BL.
Yep, it's when the rail moves. It's when, so here, I feel like I draw it. This is.
Oh, are you talking about B times
BLV
current times length?
I'm talking about magnetic field times length times speed. It's if we go to a new frame, I think it's gonna be easier to draw this. But we have, let's say we have a wire that runs like this. We have this, boop, 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 and then we have a rod here. I'm gonna redraw this because that was meant to be all straight lines. Again, here is where we do want some resistance, and boop, boop. So essentially, say we have a rod here and it's moving. If it moves and there's a current, there's gonna be a magnetic field, and this is really just, if you want to think about it, it's the opposite of Faraday's law, where now you're in changing a current, so you're having an electromotive force, and that creates a that means there must be a change in the magnetic field, which means there must be a magnetic field if there is to be a change in it, right? So again, it's there. These equations are all very much connected, which I think is in its own way kind of beautiful, but also it does get kind of jumbled up in your head, which I particularly don't like that, because if you look at other units, it's like very different, right? I mean, what are your thoughts about this?
Yeah, no, personally, um, I am going through that confusion even now because it's been a while since we've done these units. When did we learn it? Like somewhere around January, I think, right?
Yes.
Or was it before that? Or yeah,
It was
somewhere
December.
around January. So it's been a couple months, and usually all the concepts are really similar. You know, they're caused from each other, so it does get mixed up in your head a lot, especially magnetism for me, I would say.
Yes. And it's so confusing that we actually forgot negative sign in Faraday's law. We apologize that. This is represented by this is represented by Lenz's law. It's just a negative sign. We do apologize for that. And yeah, there's some actually really fascinating lore behind these equations, because the actual equation that physicists use was not created by Lenz or Faraday. It was created by James Maxwell, I believe. I don't know it's Maxwell. I don't know if his first name was James, but yeah, and that would be the second great unification of physics after Newton. So that's pretty cool, I guess. But all this unification just sort of unifies this concept into one in my head, and it's like it's kind of there, right?
Kinda, yeah.
So yeah, I mean, now that we understand the concepts, we can start sorting these equations. So, what do you think about them?
I would say Faraday's law would be kind of up there.
I agree.
It's not the best to like use when we compare to like Pivner, but maybe somewhere A or B maybe.
I feel like just because of how like cool it is and how applicable it is to our life. Because if you think about it, cars only work because of Faraday's law. So like electricity, we can only have electricity because of Faraday's law. Like all of the nuclear power plants, every way we get electricity is all because of Faraday's law. And I just think that's like so cool that I almost want to put it into S just because of that.
I don't know about S. I don't know about S.
Well, let's put it into A.
We look at such a prestigious equation like Pivner, right?
And then you get even. So what you're saying is we added a level above S and we put Faraday's law there.
I don't know about that. But A seems like a good spot for it.
Any other ones? I feel like flux has to go in the same spot just because of one relies.
Like,
yeah, we can put those two together.
Yeah.
Oh, I just realized do you want to talk? Wait, no, did we talk about this one?
Yeah, I think you did.
Did I?
We are on the Jamboard. I think you wrote it down.
Never mind then. So. Oh, we. What do you think about Coulomb's law? Actually, it's a pretty good one.
Coulomb's law has to be an S tier.
Really? Wow.
Yes. Coulomb's law has to be the key foundation for everything we know about charges. It's kind of straightforward, and in a way I really like how it's similar to gravity, because it just makes it much easier to understand, because as like physics 2 students who have had to take physics 1 before this class, in the most part, or in most cases, it just makes it so much easier to learn. And honestly, it's really, really important to how we even look at charges, how we understand charges, how we approach charge FRQs or questions that we need to use beyond equations, use conceptual thinking. So I would say it's up there, yeah, S tier.
I sort of agree with that. I am still a little hurt over Faraday's law being an A, but no, this one I can kind of understand. Again, I had this one in my dreams, so I can only say bad things about it. So
No, you can only say good things about it.
no, there are no good things.
Oh, dang.
Okay, I gotta say, I woke up from that dream in cold sweat. There's no good things about this law.
Really had to do Coulomb like that. Okay.
You know, it's just like, it's like, you know, the website Wish, where you could like buy things like for you get a lot worse version for it for a lot cheaper. This is that.
I don't.
Oh well.
Okay, keep going.
All right. eBay, right? You know what eBay is, right?
Yep.
A lot of times you sacrifice the quality for the price, right? That's
Yeah.
Coulomb's law and Newton. It's just a worse version of Newton's law. It's like
What?
it's like a ripoff. It's like a secondhand story.
But it has an extra R. Doesn't that make it better? It has R squared.
Pretty sure the other one has R squared too, I think. G1 M1 M2 over R squared. See, you guys who just took physics 1 are already better at physics 1 than us, as you can probably tell by this video. But
Isn't it UG equals negative G M1 M2 over R?
I always thought it was R squared, right? It is R squared. The force. We're talking about force.
Oh, force. Yeah.
Force. So yeah, it is just that. Just instead of a G, you write a Q.
It is exactly the
It's
same.
nice. Yeah, it's like the worst version of it. Like, I don't know.
Dang. Okay.
Okay. The concept.
Agree to disagree, Dima. Agree to disagree.
Fair enough.
It's a big part of being a physics 2 student. Sometimes you don't agree with another student. That's where Mr. Strepo says that you both are wrong.
Yeah.
But, you know.
Yeah. Real quick, I feel like this equation E equals FE over Q doesn't deserve to be sorted because it's just that Coulomb's law and the strength of the field energy combined. So, with your permission, can I delete this?
Yeah.
All right. Thank you.
No, a lot of these equations are just derived from other basic equations that are already on the equation sheet. So it's just there for ease of use, but they don't really hold any new conceptual value other than making the relationships more clear. But you can find that out if you just think about it hard enough, I guess. But you are on a time crunch, so I understand why they're on the equation sheet. But for an activity like this, it doesn't make sense to sort them.
Yep. Like again, last year I think we had a running joke that you could use Newton's second law, F equals ma, for everything and be fine with it. But you could use the other equations just for ease of use.
Yeah.
Yeah, but that's where we get with classical mechanics. So
gotta love it.
What do you love? What do you love or hate? What do you think about the strength of the field equation?
The strength of the field equation.
1 over 4 pi epsilon naught, absolute value of the charge over r squared.
I mean, I like it just because it has, again, an inverse relationship with distance.
Hold up.
And
you like those equations? I'm sorry. You like those?
Yes.
Really?
Yes, of course.
Again,
it's just something that's been ingrained into our heads every unit, that as something gets farther from something, there's less of it.
Yeah, but I see like that our little r squared at the bottom. I think not again.
It's just so easy though. When you see r squared and there's some multiple choice questions squaring it, you just know it's gonna be 1/4 of whatever it was before, not 1/2. And if you know that, you just know you have that advantage over others who didn't read the question properly and have picked a half. A lot of third graders don't know what I'm talking about, but if it's squared as the denominator, then if you decrease Dima, if you want to write it out.
So let's say we have 1 over x, right? Let's say first when x equals 1, just equals 1 over 1. But if we, let's say we have 1 over 2x, right? We multiply the bottom by 2. And this is squared. Sorry, that's what we're trying to show. We're going to get 1 over x. We're going to get 1 over 4x squared. Both of these are squared. And that's the relationship. I'm a little hurt because I was one of the people that read these questions wrong. And that's why I, again, don't really like these equations.
Oh, no. My bad. That's my bad.
Yeah, I felt personally attacked there personally. But, yeah.
Oh, no.
So
I'm sorry.
Honestly, I would say, again, my bias is coming out here, but I would say C is fair.
C? How about B?
All right, I'll give you this one. I'll give you this one.
All right.
And I'm being nice. You know, you weren't nice to me with Faraday's law, but you know, I'll be nice. Now, what do you think about this one? B equals mu naught over 2 pi current over R. It's there.
I mean, it exists,
Yeah.
and it's important.
Sometimes.
I don't really remember too much about what happened in magnetism. So
Again,
like in the magnetism unit. So I don't know how frequently we used it.
I don't think it's even that. I think just some of these equations never show up. I never remember using this equation for force. So just for that alone, I think these 3 deserve to go into the C tier. Actually, these 4.
Yes.
I'm missing this one because, like, again, we're sorting these on enjoyableness, right? Like, you have,
Yes.
like, I know I'm gonna sound like a hypocrite, but like you have these sine thetas, cosine thetas. Like, I understand Faraday's law has that, but it's like Faraday's law is just too cool. It's like I can like, it's hard, but it's like the product feels worth it. Here, it's like it gets harder, but you don't get that reward for it, if you know what I'm saying.
Yes,
Yeah.
I agree.
So I feel like all of these going to the C tier. Did we? Just 1 second. Honestly, I mean, actually, yeah. All right. So now we have a more fun unit, circuits. So you wanna take it away?
For circuits, yeah.
Yeah. Great unit.
So basically, I know I've said basically way too many times, so I'm not gonna start with basically.
But basically, circuits.
Circuits, they're the most important equation in circuits has to be hands down V equals IR.
Also known
So
as
let me draw that
also
out
known
for
as
you.
Ohm's law, which is what gets used around quite a lot.
What
Ohm's law.
does?
Ohm's law.
Ohm's law.
And
Right.
this only works for ohmic devices, which we usually assume they are. A lot of devices are near ohmic, but also, just to be real quick, ohmic devices do not respond to temperature much.
Yeah.
And this it gets used for this. And this is the holy grail of circuits.
Oh yeah. Because so usually there's like questions that tell you the voltage of a battery and gives you the resistance of maybe a light bulb and asks you how much current goes through that light bulb, and we're gonna get into that later, but it's used in so many different circumstances, especially in complex circuits where we have to use different rules like Kirchhoff's rules. I can dive into that now if you want, or is there anything else
Let's briefly talk about how circuits look. So, and
how circuits look?
Yeah, and yes, the different parts of a circuit. Because
Okay, yeah.
in a circuit, we have first of all we have wires, which is just a line. If my pen would work, I could maybe draw it, and it does. So this is a wire. It carries charge. Charges move through it. Pretty self-explanatory. Then we have a battery, which is where all our charge comes from. And we represent it by a big line, which is the positive charge, and a small line, which is the negative charge. There's the wires that come off of it. Then, this is where the V comes from. The current obviously is related to the wires. It's what goes through the wires. And then we have resistors, which look like mountains. And those, as the name suggests, resist charge, right? And the charge moves a lot slower through them. And last but probably least, because I didn't really like them, but we have capacitors, which store charge. So those are equal lines. And so in the beginning, when they're not charged, so here, let's draw our first circuit. Let's say we have a battery here. There we go. Obviously, this is the positive end. This is the negative end of the battery. Initially, when the capacitor is not charged, the wires are going to go through, they're going to get across this little gap, and they're going to come across. Over time, the capacitor is going to get charged, which means that the charges, there will be less charges here. So over time, charges accumulate on these plates and less charge flows through. So a really long time later, long time later, the current will stop flowing. And the potential difference here is going to be the same as here. And those are capacitors. And yes, now we can take it away with Kirchhoff's laws on the next frame.
All right. So Kirchhoff basically had two rules. So the first rule is called the loop rule. So the loop rule tells us that the voltage around a closed loop. Wait, I can just write this out. That'd make life so much easier. Tells us that the voltage around a closed loop is 0 volts.
The changing voltage. I'm again being a stickler here, but
what happened? Change in voltage?
Change in voltage.
Oh, right.
Yeah.
Change in voltage. You're right. No worries.
Yeah.
Okay. Change in. I don't know how to type triangles, but so I'm just gonna say the change in voltage around a closed loop is 0 volts. So what can a closed loop possibly look like? So a closed loop could be something like we got a battery right here, and then we got that. We can have a little light bulb, I guess, whatever. Yeah, that's the light bulb, if you couldn't tell. So this could be a closed loop. So around this whole closed loop, it needs to have 0 volts. The change in voltage needs to be 0 volts. So another example of a closed loop in a more complex circuit could be something like, got the battery right there. All right, it's going like this. That's something there. We got one light bulb, and then here, and we got another light bulb. We got that, a light bulb there.
Can you stop for a second? So
yeah.
You have this little branch here. Can you explain how that works? Like.
Oh, right.
Yeah.
So this is basically, this branch makes the whole circuit a parallel circuit, and it's basically called a junction, right?
Yep.
And what it does is the current that goes to, I'll just say this is light bulb 1 and this is light bulb 2. The current that goes to light bulb 1 and light bulb 2 will add up to the total amount of current that is being passed through the circuit. Whereas if it was in series, like the example we had above, we'll just say this is light bulb 3. the, and say we add another light bulb here called light bulb 4. Here, since there's no splitting and it's just all in line with each other, the current being passed through this, through light bulb 3 and light bulb 4, would be the same. Whereas if we looked at voltage, it's actually flipped. So since, if we go back to the example down below, since it is parallel, since there is a junction, the change in voltage will be the same for light bulb 1 and light bulb 2. However, since the circuit that is in series up top is in series, the change in voltage would need to add up to equal 0. So they would be, so that the change in voltage for light bulb 3 and the change in voltage from light bulb 4 would add up to get the change in voltage through the whole circuit, which can be, which the total change in voltage is usually set by the battery and the voltage that the battery has. So, was that correct? Did I miss anything for an explanation for parallel and series circuits?
No, and you actually managed to fit in the explanation for Kirchhoff's second law, which states that which is called the junction rule, and it is essentially says that the current into a junction has to equal the current out of a junction. So the current, let's call this current here I1. Let's call this current I2, and this current I3, and we'll call this I4. And so essentially, I1 is equal to I2 plus I3, which must also equal I4. And this is essentially the conservation of charge it's the concept of it's the explanation for the conservation of charge in circuits. Because obviously charges goes in, those charges must come back out, right? Obviously. And yeah, I mean, you nailed it with the explanation of parallel and in series circuits. I want to briefly touch back on how this changes the other values besides current. So it's probably actually best to just go back to the tier list, because here we have the equations for how capacitance changes. Actually, let's talk about capacitance real quick. I'm sorry, I'm jumping around here. There's a lot to cover with circuits. It's was it the biggest unit?
One of the biggest, yeah.
It was very long.
Definitely.
Yep. So there's a lot to cover. Again, all concepts are very related. So it feels like a mess, when in reality it's just like, it's like a salad, if you want to think of it like that. It's like a nice big salad, potato salad, if you will. And yeah, so capacitance is equal to charge, which again we use Q, not the first time we've seen this letter, times C, which is the capacitance, times delta V. This is the way I like to write this out, just because it's nice to remember. Oh, QCV, just nice to remember. But if you want to arrange it, you can say Q equals I. You actually cannot say. You can say delta V equals Q over C. You could say C. You could. Am I okay? I am okay. Yep. You could say C equals Q over delta V. And yeah, that is sort of really it for capacitance. Then now let's go back. Let's talk about, so capacitance in a series circuit. You take the inverses. So 1 over CS is equal to 1 over CI. So this is the summation. So essentially, you take the inverses of the values for capacitance of each capacitor, add them up. That's your inverse of the whole capacitance. In a parallel circuit, it's much easier. You just add all of them up. That's your capacitance. Resistance is very similar in that regard. If I can, with the image, that would be very appreciated. For resistance, for the parallel ones, you take the inverses, add them up. That's the inverse of your resistance. For the series, you just add up the resistance values, and that's your resistance value. But then you might be wondering, well, that's cool and all, but what is the resistance? How do I calculate it, right? Because if I can add up the resistances, well, what are the resistances, right? Well, resistance R, let's call it R. Resistance R is equal to rho, which we know to be density, I believe. Should still be density here. Rho L over A, where L is length and A is area. And that's for each individual resistor. So coming back, let's say we have a circuit, we have a battery, we have resistor number 1, we have resistor number 2. Coming back to Kirchhoff's first law, let's say this has a resistance of 5, and this has a resistance of 4. Obviously, this means that the potential on the battery, assuming the battery has no internal resistance, in which case it's gonna be a little more than 9, but there should be 9 volts. That's it for resistance. That's it for parallel circuits. That's it for series circuits, I believe. We can touch a little bit upon energy, I guess, which is this looks very similar to,
also one more thing. Sorry to interrupt.
Oh, no worries.
When you were talking about rho, can you go back to that slide real quick?
Yep, right here. It's right here.
Right there. Okay. Yeah. So I think that is resistivity.
Oh, yep. And that is individual for each material, I believe.
That makes sense. It's just a property of different materials.
Sorry about that, but yes.
No, you're okay.
All right. And then I guess we can briefly touch upon internal energy. This is gonna look very similar to kinetic energy from physics 1. So C delta V squared. And because of that, we can also, if we want to rewrite it as 1/2 Q delta V. And that is the energy in the circuit. Is there anything else we have to cover here? I don't believe we do.
No, I think that's it for circuits. One
more thing. When you're trying to find the amount of charge and the capacitance across between two plates. So if you go back here, real quick, there's my capacitor. So if you wanna, this can be when the capacitor is charged. It can be represented by the capacitance, amount of charge, is equal to K, which is, I believe it should be, it's the dielectric constant, which is individual for each material, times epsilon naught, oh, that's a weird epsilon, times area of the plate over the distance between the plates. So that is just another way of finding capacitance. It's pretty useful, I would say. It didn't come up that much, to be fair. But yeah, I think that's it for circuits, actually.
Yep. Let's get to ranking.
Let's do it. I feel like the series and parallel should both capacitance and that should just go into one thing. Same principle.
Just make them one group.
What do you think about them?
I mean, they were used a lot, at least in our circuits unit, and they were also not that hard to use as long as you identified Kirchhoff's rules and you knew what equation to use for what circuit, what part of a circuit. So I would say it was pretty. It was definitely above average, but not by much. Because when you compare those equations to other equations, I don't think it can be comparable to like an A or S tier equation. So probably B would be good.
I would agree with that. I feel like the equation. First of all, where's V equals IR? Oh, we forgot to talk about power. So if you want to look at the brightness of a, like if you say you have a light bulb, the brightness is equal to the current times the change in potential. So across the light bulb. So obviously, I mean, the more charge you're gonna have in the light bulb, the brighter it's gonna glow. Pretty self-explanatory.
Yeah.
I think Ohm's law has to go into the S tier personally. I mean, it's just
Ohm's law.
V equals IR. I mean, it's simple, but it's also just it's simple, but it gets used a ton. It like unifies so many concepts around circuits that it's just like
Yeah, no, it definitely should. It's like the
it's my second favorite equation.
It's like
probably.
Yeah, it's like the monomer of
Yeah.
the circuits physics unit. And for you third graders that don't know what a monomer is, it's basically a small building block of stuff in the body. I'm not going to go into specifics, but it's a small building block
of
inside the body that
of a
can
bigger
be
molecule. Not necessarily the body, just a bigger molecule.
What?
Just a bigger molecule, really.
Right, yeah. It's basically like a molecule in the body that can be put together to make a bigger molecule in the body.
Think of it as a really big Lego structure. A monomer is an individual Lego. That's really it. Like everything revolves around it, the combinations that you do with this.
Yeah.
Yep. So, speaking of power, actually, what do you think about the power equation? Because it barely came up.
The power equation barely came up. I think it's better to have it like in the back of your mind because sometimes FRQs will ask, oh, which light bulb is brighter or something. And then you don't want to talk about the light bulb being brighter because of current, but you want to make sure to bring up the fact that maybe current's the only thing that changes the amount of power that goes through the light bulb because the change in velocity the change in voltage is the same. So the fact that you need to explain it makes it important, and the fact that power is what truly dictates the brightness of a light bulb is important, but you don't really need to. It's really easy to learn, and you're gonna have it in the back of your head. And though it's not explicitly brought up sometimes, it is important to have, I would say.
I feel like it's a D tier, to be honest. It's like it's not impressive.
D tier?
Yeah, it's like P equals I delta V. It's like it's not impressive. You're not impressing anybody with that.
It's not impressive. I agree with that. Yeah.
It's like
it's definitely not impressive.
The more charge you have, the the brighter the light bulb. Like, really?
What?
That's like.
I never would have known.
Yeah, it's like if you blow harder into the balloon, it's gonna inflate more. Like,
what?
It's like it's like like when like you're playing against somebody and like you're losing and like you say like, oh, I'm like really bad. Like I'm not doing that great, and like somebody just tells you like, just be better. It's like that.
Sure. Yeah.
Yeah.
You know what? Yeah.
I feel like this video is just me like slowly like projecting like my childhood trauma, but
physics is a part of that. As much as I love physics, there is a lot of trauma that goes with it.
That is true, and especially in electrostatics units, which thankfully those are behind us. We'll get there. We'll get there eventually. Eventually.
If we have enough time.
We have plenty of time. Optics is pretty quick, I think. So resistance, I mean, again, it's pretty quick. I mean,
Average.
never used it. Yeah, C tier is fair, I guess. Similarly, I think current is the current equation is C tier because it's a pretty simple concept. It's not that cool because it just makes sense. Right?
Yeah.
Yeah, I feel that's a quick C tier. And the capacitance equations. I mean, I did not like this one with the dielectric constant times uh electronic oh, English hard. um the dielectric constant times epsilon naught a over d. I mean, it barely gets brought up.
We really didn't use it, especially because of the whole dielectric constant part of it. Like, it barely was used. The only thing it's really getting at are how dimensions of a capacitor affect its capacitance.
You
But
might,
yeah,
I think it's the
I
only
mean,
I think it's the only equation that didn't come up on the EP test.
yeah, it barely comes up. It's important, and if you get a question on it, that equation is the only way you're gonna get it right.
I think it's an F
Unless you're
tier.
like superhuman.
I think it's an F tier. I'm gonna be honest.
Yeah, it's S tier though.
Nobody likes you.
Dang.
Yeah.
Really had to do that to the equation.
It deserves it, to be fair. And you have the superior equation that has capacitance in it, and it actually gets used quite a lot. It you can analyze more about the actual circuit with it, not just the actual properties of the capacitor. There are no specific components that change based on the material that you're using. For that one, I think it has to be at least a B, to be fair.
Yeah.
Yeah, so that's a good, nice little B we have. And that is it for circuits, actually. I'm just looking back.
Nice.
We missed quite a lot of electrostatics equations, but actually we talked about this one just now. What do you think about the energy equation?
It's important, but we didn't really do much with it.
I think it's a D equation, just
Yeah.
has that vibe to it, you know?
It's really important just because it's energy, I would say, but we also didn't really use it, so it's kind of irrelevant.
Yeah. Then we have V equals KQ over R. I mean, it's just a definition of potential, which I know we didn't cover on like our little Jamboard, but like, in all honesty, you don't need to use this. It's just it defines electric potential, which I guess if you wanna define it mathematically, it's kind of nice, but it's really just the amount of work energy needed to move an electric charge from one point to another in a field. So it's not really impressive. You're not impressing anybody with it. So
Yeah.
So I mean, again, I feel like this is an F tier equation. It's just like it doesn't get brought up. I mean,
Yeah, and it's so similar to some of the other equations. Like, if we look at the strength of the electric field equation, like, it's very, very similar, except for the fact that on that equation, I'm pretty sure the R is squared. So,
I mean, if one of you guys likes defining things like mathematically in your head, that this should be higher up for you. But again, this is our personal tier list. You're free to disagree. I disagree with I disagree with Faraday's law being only an A tier. But for me personally, I never enjoyed using this. I don't ever actually remember using it. And yeah, now we have a couple equations that use potential that we didn't cover, but that do relate to electrostatics, where the internal energy is equal to the charge times the change in potential. What do you think about this one?
Internal energy equals charge times change of potential. I mean, I don't really remember when we used it. I mean, I would say D tier.
That's fair. I don't have any strong feelings about it. I mean,
I know it's important,
Not really.
and I know I've used
Out
it.
of the equations that are up here, I think it's on the importance. If we're sorting them by importance, it's pretty low. If we're sorting them by how fun they are, like if you tell me you have fun using delta U equals Q delta V, like you're joking. You're joking. Like
You've got to be trolling.
You have a weird sense of humor. Like you're trying to be edgy. That's it. I think the same thing goes for the strength of the field equals delta V over delta R. It's the same thing. Again, you're just trying to be edgy. I mean, it's like, it's there. I mean, as a concept, it's nice. As a reference point, it's sometimes okay. But nobody says that their favorite equation is delta V over delta R, absolute value of that equals the strength of the field. Like, no.
Yeah.
And similarly, E equals Q over epsilon, not A. But what are your thoughts about this one?
It exists. Like, I don't, like, some of these equations are just so jumbled in my head. It's just because there's just so many for electrostatics and magnetism that a lot of them just you don't really remember after you're done with them. Yeah. And that just talks about its like how significant it was to you, how much fun you've had with it. Like, if you had a lot of fun with the equation, you would remember it. If the equation was very important, you would remember it. I'm not the best physics student, but I'm not like utterly bad. Like I still study and stuff. So like I would say I know my way around what equation's important and what equation isn't. So this definitely does not make the cut. I would say DRAP.
If I remember correctly, is this no? Never mind. I am being dumb. Just kidding. I would probably agree with this. Yeah, yeah, let's put it into F tier. We don't have enough F tier.
Yeah.
Now we got.
We're being too nice to these equations.
Yeah, you know, except Faraday's law. You know, Faraday's law, like fantastic.
Okay. Okay.
I might just put a poster of Michael Faraday in my room soon. At this point.
Michael Faraday. What does he look like?
Also, Michael. Great name is Michael. I gotta say.
Michael Faraday.
Anyway,
okay.
I think that's enough obsessing about Faraday for now. Let's talk about optics, right? So,
yeah,
pretty fun unit, I gotta say, except for some parts. It's a really mixed bag.
I don't know about that.
I don't know. There were some good parts. There were some bad parts. We're gonna get to the good and the bad. So yeah, let's start, right? I think we can quickly sort out the couple of the easy equations, like n equals c over v. Just really, actually, is it this? Just speed of light. Really, it's like these equations. The speed of light, index of refraction. I mean, it's not really a hard equation. You don't use it that much. What do you think about it, Sai?
I would say that, yeah, like you said, it's not really used too often. It could be useful for a few derivations here and there.
True.
And the equation itself just, makes sense at first glance, because where you're basically seeing how the speed of or the velocity of the light compares to the speed of light that we know, which is 99 if I'm not, or 9 to the power of 9.
The speed of light?
If I'm not mistaken.
That seems...
Wait. It's sorry, 3 to the power of 8. 3 to the power of 8. Yeah, 3 to the power of 8. That's what I meant. Yeah. So, yeah, it makes sense, but I would put it maybe in a C or lower, though. Just because it's not really too relevant.
For context to you guys, me and Sai both took AP Chemistry this year, where we did use this equation, so I didn't really like those parts of AP Chemistry. It just felt boring, so I think this kind of comes across here. I feel like a D is fair. Would you agree?
Well.
Right. Let's move on. I mean, we could talk about some wavelength equals velocity over frequency. Again, I don't think this is a particularly complicated equation that we need to go in detail. Just, I mean, not much.
I would put it the same as N equals C over V.
I would agree with that.
Just because they both are pretty basic.
I would agree with that. So let's continue talking about linear optics. Let's linear optics. Sorry, geometrical. Well,
optics.
Optics, yeah, optics. Just let's actually, yeah, we're going back and forth, right? It would be wrong to go in ourselves talk about different ones. That's why let's jump to ray diagrams, right? Because jumping around is fun. I could do a quick drawing, I suppose, for our viewers here. So, with ray diagrams, as you might expect, you're drawing rays of light and how light behaves. So say we have an object, and let's say we have a concave mirror here. This is obviously exaggerated so that it's see, and let's look from the top. You would draw, this is usually how you draw a mirror. So you have your ray number 1 goes perpendicular to this axis here, and then there's a focal, let's assume the focal point of the mirror is about here. We'll call the focal point F. That's what it usually is. This ray goes to the focal point and exits and goes until infinity. And this way we're looking at light as a particle, because in this case it does behave like a particle. Once we get into the more nitty-gritty with modern physics, we're going to see that light is not a particle, it's not a wave, and it's actually neither, and it's made of particles called photons. But we'll get into that in a second. Then we have this ray that just goes here. Sorry for that one. Yeah, I'm going to redraw that little thing. It goes to where this axis meets the mirror and bounces off at the same angle as this. So we go here, and there we go. Same angle. And actually, you could stop here if you wanted to. But if you want to, you could draw another one. Goes through the focal point, bounces off perpendicular to the ray, to their axis, and they all meet here. And this is where the image is going to be. So this is just sort of an example of what you do, and this is represented by the equations, by the magnification equation and the distance. Actually, is it this one? Pretty sure it's this one too, right? 1 over si plus 1 over s naught equals 1 over f. I think that's one of those two.
Magnification.
Magnification is this one, which I actually...
I know it definitely can be used for lenses.
Oh, lens. Yep, there we go. Obviously, lenses, mirrors, sort of like the opposite. One, you guys know lenses, like magnification, those, like, essentially magnifiers. I like to think of these things as cameras, like sort of like enhancing, like making an image bigger, smaller. So, what do you think about these equations, Sai?
I would say that the magnification equation is very important. So, say you messed up on your ray diagram, and you know that you messed up, but you don't really know how you messed up, right? Yeah. And the question is talking about how a certain image is formed, or a question is asking basically what the image is going to look like. Is it going to be enlarged? Is it going to be inverted? So the answer for that can be found using the magnification equation and just seeing what the magnifying value is. Is it more than 1? If it's more than 1, it's enlarged. If it's less than 1, it's reduced. And if it's positive, it's going to be upright. And if it's negative, it's inverted, if I'm not mistaken. Yep. So it's a really nice backup to have if ray diagrams don't work out, or even an alternate method of solving those types of equations, especially when those types of questions, especially when you don't have the time to make drawings and you just want to find the answer quickly.
Yep.
So I would put that at A or B tier.
Yep. I tend to agree with that. I would say A is a good one, especially for me. I'm not a very artistic person, so often my lines and angles come out looking circular instead of like actual lines, and so because of that, I find this equation to be really nice for that. So I would say an A tier is probably fair, right?
Yeah.
Yeah. And yeah, let's keep bouncing around. This time let's go to Snell's law. Obviously, that correlates the index of refraction to the angle. So essentially, when you have an object, I can draw it out real quick. Let's say we have an light going from one medium to another. The angle at which it enters is gonna change how it's gonna look. So we actually ran out of frames. That's how extensive this podcast is. But let's say we have one medium on the right. Let's say call this M2. This is M1. And we'll have our normal line, which is just what we're going to be comparing. RA2. And let's say RA enters like this. Here, let's think about, so we have our N1 sine theta equals N2 sine theta. So obviously if the index of refraction is bigger in this medium, that means the angle has to be greater in the second medium. So it's gonna come out looking like this. If the opposite is true, it's gonna come out more looking like this. And this angle is gonna be smaller than this angle. That is essentially it. I find it to be a pretty easy concept. What do you think about it, Sai?
Yeah, I think just like a really simple way of understanding that equation is if the index of refraction is higher, it will make the line closer to the normal. Whereas if the index of refraction is lower than the previous index of refraction, then it will be less closer to the normal, which would make it deviate out rather than bending in towards the normal.
I'm feeling I'm feeling a B tier on this one, you know.
A B tier, yeah.
It's just like it's a solid, nice equation. Like I'm not gonna complain about using it, but I'm not gonna be like, oh, this is a fun question, you know?
Yeah.
Yeah.
It does get you through a lot of multiple choice questions, though.
That is true.
Because I know that at least on our practices, there were a lot of optics questions, and using or just understanding Snell's law. You don't even need to use it, but just understanding it really gives you an edge time-wise, because you can just get the answer to those equations real quick, or those questions real quick.
Yep. All right, let's move on to this equation. I believe this one talks about lenses, right?
Yes.
I have the same feelings about it as the magnification. Just 1 over distance of the image, 1 plus 1 over distance of the object equals 1 over the distance to the focal point. I mean, it's pretty simple. Nothing too major, nothing too special.
Yeah.
So,
I would agree. It's pretty basic. If you have an FRQ in optics, you're most probably going to use this equation somehow. Maybe in a derivation.
Yep.
Or just trying to find the focal point. But you definitely will use it.
And
so
often optics, at first, they're very complicated, but thanks to these two equations right here, especially ray diagrams, like at first I thought they looked really hard, but often you can get away with just using these two equations, which is always nice.
Yep.
So now let's talk about the double slit experiment, right? Because we all love it.
Yes.
This proved the particle theory of Newton, and it was then after this experiment, it was proposed that light was actually a wave instead of a particle, which Newton would eventually disprove, but we're not there quite yet. So let's say we have a light source here. Let's give it a nice red color, and we have a wall here, and we're gonna see that as the light waves, I suppose, because in this case light does behave like a wave, as the light waves travel, the point where there's constructive interference is there's gonna be a light. So let's say this equals n equals 1, and we're gonna see this like all throughout this thing, and this is represented by x equals m lambda L over D, if I believe, right?
Yeah.
Yep. This equation has this is an n, sorry, not an m. Both are used often depending where, but it just really this integer right here. This formula has 3 variables for distance, which already makes it an F tier in my opinion. I mean, like I think this distance is represented by L. Obviously lambda represents wavelength, as it always does. This distance should be x, I think, right? Distance between the slits is x.
Yep.
And then D, if I remember correctly, is the actual size of the actual split, right?
D.
Or is it this distance right here? I think this might be it.
Yeah.
Yep.
I think it's that.
Yep. And yeah, I mean, like, why would you enjoy? Like, nobody enjoys this one. It's not even on the equation sheet. It's a pain to memorize. I mean, with your permission, can I just chuck this straight into the F tier?
Yeah.
Yep.
There's way too many variables for distance, and often you get them confused. Even though they're talking about different distances, just remembering what variables are for what distance that is being measured, it's just a pain.
On a similar note, can I chuck these 2 equations here? They relate to this one. I think you can get the one that we just talked about from these 2. Just like,
yeah.
It's easier to memorize that equation, and it's gonna be like just that one odd question that nobody's gonna like. There's a couple of questions on this on the AP test, and they were not fun questions.
Yep.
Well, but speaking of Newton, let's talk about it. You wanna talk about him, Sai?
About Newton?
Oh, Newton. Oh, Einstein. You know.
Einstein. Okay.
Yeah.
So, basically, probably the most famous equation that we know that pertains to Einstein would be E equals mc squared. And E equals mc squared basically is used to find out how much energy is being released if mass is being lost as atoms go through different phases, you could say. Not phases as in not states of matter, but just like different decays. So like alpha decay, beta decay, any other decays as well. So yeah, I would say E equals mc squared is pretty important when it comes to a modern physics question. I know modern physics questions are usually pretty limited, but E equals mc squared has to be one of the more important ones, and it's not really hard to apply, nor is it really hard to solve. So I would put it maybe in an B.
I think just because of how cool it is, because like this is like the equation in physics, or it often feels like it, and you often hear about it, and it's like you finally get to figure out what it is. Just because of that, I think it's a solid S tier.
S tier.
Because it's E equals mc squared. It's like all this work leading up to it, and you get there and you're like, oh wait, this kind of makes sense.
You know what? Sure.
Yep.
You gave me Faraday's law. I'll give you this.
You didn't give me Faraday's law.
Right.
Oh no, I'm saying I see. I mean, if you want to put Faraday's law up top, you know, they're like, I mean, I'll be happy.
I think I'm good.
And
All right.
last but maybe least, but I don't think so personally, let's talk about the photoelectric effect. So for this one, we're gonna bring up the good old trusted diagram. And let's say we have a light source right here. I'm gonna draw this out in yellow this time. We have a light source here, and let's say that we have a capacitor, we have a quick little battery, and let's say the current is going this way, right? Actually, no, not bad. Let's say the current is going the other way. Just gonna be in there. That is the same way. So let's say current is going this way. And so that means charges are moving, obviously, between the capacitor, they're moving from right to left. Then, let's say we have light. Actually, wait, did it? And let's say we have, let's say we have some light, because this analyzes the interaction between a photon and an electron. And this is what Einstein discovered and used to show that light was not a wave and it had some particle-like properties. So essentially, when let's say we have a photon and we have an electron, when a photon interacts with an atom, an electron goes to a higher state because it often absorbs the energy. Alternatively, the electron bounces off. But for here, let's assume that it's a strong enough photon that it excites the electron. That means that when the electron gets emitted later, there's energy released. And here we can actually convert this to kinetic energy. So for example, this often means that in the circuit, electrons can go against the current. So let's say light goes here, electrons are moving here, and they're fighting against the field because the field is pushing them this way, but their velocity is already moving them this way. And it's just a matter of can they get across. And that is really the photoelectric effect, simply put. As a concept, I actually think it's pretty cool, but what do you think about it? Sai?
Yes. I am thinking.
Well,
I think I would say, I mean, it's used, but I don't know to what extent it really is used. Like, is it really important enough to be in one of the higher levels? Do we really use it that often?
but I suppose on one hand, yes, but I guess it's an abstract concept. It's sometimes hard to grasp your head around it. You don't really have fun with it. You might be wondering what this in this equation what the phi represents. That's what this little letter is. It just represents the work function, which is a
Material property.
A material property that is obviously individual for every material, and this measures if the electron can get across. Really, obviously, F is frequency, so wavelength is gonna matter. That's why when I said more energy photons with higher frequency, meaning shorter wavelengths, are gonna have more energy. Obviously, as we can see by this equation. I don't really have strong preferences. I would put them all in the D category, all of these. Actually, these two.
Yeah.
These two. And then the last one talks about, alright. Oh, that is not what we wanted to do.
The last one, do you mean wavelength equals h over p?
Yes, the how a photon can have momentum despite having no mass, which is an interesting concept. Obviously, this is modern physics, and modern physics when talking about physics 2 is very abstract. I don't have strong thoughts about this equation. I don't remember ever using it, to be honest.
I remember using it a few times, but it's definitely not too significant.
With your permission, I will put this into the F category.
The F category? It's not as bad as some of the other ones in the F category, though.
We'll put it at the top of F. How about that?
The top of F.
The
sure,
top of F.
That works.
It's like he showed up to class, he failed all the tests. That's what
unfortunate.
Yep. Well, and that is it. That is physics 2.
All right.
Thank you guys for watching. Hopefully we're back next year if all goes to plan. If we're not, hopefully we're safe.
We will self-study and still put out one of these, even though it doesn't count for a final project.
Yep. And yeah, I hope you guys learned something. Hope you guys had fun, and thank you.
Yeah, thank you. Bye, Dima.
Bye-bye.